In this video, we're going to look at the product rule. The product rule allows us to find the derivative when we have two or more functions multiplied by one another. Hence its name, the product rule. An example might be now if we have y is equal to x cos x. We have now two functions of x. We have x, which is a linear function, an algebraic function, and we have now cos x, which is a trig function. We might have y is equal to e to the x multiplied by sine of 2x. So two different functions. We've got now an exponential function and we've got a trig function. We might have y is equal to 3x squared multiplied by the natural log of 4x. So this time we've got an algebraic function and now a log function. In general, if we have y is equal to u multiplied by v, where u and v are both functions of x, we can say the derivative by the product rule will be v multiplied by du dx plus now u multiplied by dv dx. If you want to read this out, we take the first function and multiply it by the derivative of the second. We then add to that the second function multiplied by the derivative of the first. So we can see now this is the first function multiplied by the derivative of the second, plus now the second function multiplied by the derivative of the first. If you want function notation, we can say the derivative with respect to x of the f of x multiplied by the g of x will give us now f of x multiplied by g dashed of x, where g dashed is the derivative of the second function, plus now g of x multiplied by f dashed of x. So that's using function notation. So in this particular case, we could say that x was the u and cos x was the v. We could say the u was e to the x, sine 2x was v, and so on and so forth. It would be tempting to think that if we have a product, we just find the derivative of each and multiply them by one another. As we can see here though, that is not the case. And we can show this with a basic algebraic function. So if we now have y is equal to, let's take x to the power of 6. I could write this now as a product, and I could write this as x to the power of 4 multiplied now by x squared. So let's see now how the product rule would work. The way I like to do the product rule is have a little grid. You certainly don't have to do this, but I think it helps in terms of keeping on top of your work. So what we're going to have is u just here. So if I now take u to be x to the 4th, we've got now its derivative du dx. So I'm differentiating now u with respect to x. That's going to give me 4x cubed. If I now take v is going to be x squared. If I now take the derivative with respect to x, which is dv by dx, we're going to end up now with 2x. So by the product rule, we multiply v by du dx. We then add to it u multiplied by dv dx. And this is why I like the little table. You certainly don't have to, but it's an option. So what we've got then is dy by dx will be equal to v multiplied by du dx. So we're going to have x squared multiplied now by 4x cubed, and then we're going to add to this now u multiplied by dv dx. So we get x to the 4th multiplied now by 2x. So if we tidy that up, the derivative dy by dx will be equal to, if I have these right here, that's going to give me now 4x to the power of 5 plus now 2x to the power of 5. If we tidy that further, adding now these terms, dy by dx will be equal to 6x to the power of 5. Now if we look back right here, what we end up with now, differentiating x to the 6, we know quite clearly from this that dy by dx multiplying down by the power and dropping the power by 1 gives us 6x to the power of 5. So you can see that this now works with a basic example. Yet if we'd gone the other way and just found the derivative of each of these, we'd have 4x cubed multiplied now by 2x. So that's going to give me now on here 8x to the 4th, which is quite clearly incorrect. So all I've done here now is applied the product rule. In this video, we're just going to work through some basic examples using the product rule. In later videos, I'm going to dedicate a whole video to differentiating trig functions and also one to differentiating exponentials and logs. The idea of this video is to build up a basic understanding of the product rule. So let's go ahead and look at something that we might have dealt with in the past. Let's say we had now y is equal to x multiplied by x plus 1 all squared. We would have now expanded the brackets, multiplied through, and now differentiated term by term. But what, for example, if we had now y is equal to e to the x multiplied by x plus 1 all squared? We could treat this as a product. So let's go ahead and differentiate this. In the first video, we looked at building up standard results. So what we're going to have then is now u will be equal to e to the x. So we've got u is equal to e to the x. The derivative du by dx will be e to the x, and we see this now as a standard result. If you're not comfortable with that, please do check the video prior to this one, and that's got some information on that one. What we're now going to do is take v. Now v is x plus 1 all squared. For this particular case, we're going to use the chain rule. So we can see using the product rule sometimes requires us to use the chain rule as well. It's not a feature of the product rule per se, but it is now something that we might come across. So what we want then is dv by dx, the derivative now of v with respect to x. So all I've done, I've let u be equal now to e to the x. I've let v be equal to x plus 1 to the power of 2. So let's go ahead and use the chain rule. We differentiate the outside function, we rewrite the inside function and multiply through by the derivative of the inside function. So in this particular case, we multiply down by the power, we rewrite the inside function, we drop the power by 1 and multiply through by the derivative of the inside function by the chain rule. So we end up with 2 lots of x plus 1. And again, if you'd expanded that out, you would have got x squared plus 2x plus 1. The derivative would be now 2x plus 2. So what we want to do then is find dy by dx. So by the product rule, dy by dx now is going to be, and let's just scribble this down, we're going to have v multiplied by du dx, and it doesn't matter which order you do these in, we're going to have now v du dx plus u dv dx. The reason I choose it this way round is when we come on to the quotient rule, the v du dx generally will come first. Now I prefer to put it up first for both. It's entirely up to you though. So let's go ahead. We're going to multiply these two. So we can say now that dy by dx will be the product of v multiplied by du dx. So we're going to have now e to the x multiplied by the quantity x plus 1 all squared. We're now going to add to it the product now of u dv dx. So that's going to be now 2e to the x, and then we'll have x plus 1. We can of course factor this, so let's go ahead and factor that. We can take e to the x out and then x plus 1. So taking the common factor of e to the x, x plus 1, that's now going to leave me here with x plus 1, and then we're going to have just here, we're going to have now plus, and we will have the 2. So all I've done now is factor that. So let's check we've got all of that. That's going to, and let's just put that in to make it a bit more obvious. So we've got now e to the x, and then we've got x plus 1 multiplied by x plus 3. So at this stage here, we found the derivative. All I've done at this stage now is factored it, and that's something that you've looked at before. So if we have the product now, e to the x multiplied by x plus 1 all squared, we can use the product rule. And I've done that particular case as we've got now a function of a function to deal with as well. That might not always be the case, quite clearly it's not always going to be the case, but it's good to recognise that you will sometimes have to employ more than one rule. So let's work through a few basic examples of this. Let's now take y is equal to, and we'll have now 2x, and then we'll have e to the x. Now in terms of this one, what we can do, we can leave the 2 in, or we can take the 2 out. It's entirely up to you on this. So what we could say then is the following. We could say that dy by dx, and I'm going to take the constant out, dy by dx is going to be equal to 2 lots. So what we're going to have then, our value of u, and we'll put it just here, u, we're going to have x. The derivative du by dx will be now 1. If we now consider our v term, I've taken v to be e to the x. The derivative dv by dx using one of our standard results will be e to the x. We multiply these two and we add to it the multiple of these two. So we get now one lot of e to the x plus now x multiplied by e to the x. So by taking the 2 out, I'm not having 2x and 2, I'm just having 2 lots now of this quantity. So we can write that dy by dx, and we can factor this. We can take a common factor of e to the x out, so we have 2e to the x, and then we'll have 1 plus x, or x plus 1. Entirely up to you on how you want to write that. So that now is the derivative of the product 2x e to the x. We might have had a function of a function with e to the x. So let's say we had, let's do a different one. Let's say we had now y is equal to x squared, and then, in fact, let's make it 7x squared e to the 3x. So we can see now that we got a function of a function. So what I'm going to do is use the chain rule informally now to find the derivative. So we've got now dy by dx, and again I will take now this constant 7 out. So setting up my table, and again you can decide whether you want to use this or not. What we'll do this time is use function notation. So what we'll say then is the f of x will be equal to x squared. So f of x is x squared, so the derivative f dashed of x is going to be 2x. If we take the g of x, the g of x is e to the power of 3x. Using the chain rule, we can say g dashed of x is going to be 3e to the 3x. If that's new to you, do check out the video prior to this on the chain rule. So we take now g of x and multiply it by f dashed of x, and then we take now f of x and multiply it by g dashed of x. So what we're going to get then is 2x, just here, 2x e to the 3x. That's simply multiplying g by f dashed, and then we'll add to that now, we'll have now f multiplied by g dashed. So we'll have 3x squared e to the 3x. And then all we'll have to do now is factor this. So let's go ahead and factor this. So our derivative dy by dx will be now 7. I've got a common factor of x e to the 3x. So we can take x e to the 3x out. And that's going to leave me now here 2 plus now 3x. So all I've done is taken out the common factor. So we're left now with this scenario. Now, if we were asked where this particular function was stationary, then we could set this to 0. So when we've looked at stationary points in the past, we know that the derivative dy by dx would be equal to 0. So if we were asked to find where this is stationary, we could consider the following. We could say now, and I'll write it just here, for stationary points, dy by dx will be equal to 0. So from that, we can see now, if I set this to 0, we've got now 0 would be equal to, and then we've got the 7x e to the 3x, and then we'd have now 2 plus 3x. And we might be given a domain for this particular function. For now, I'll just treat it as is. So in this case, we can see now that either x would be equal to 0. We could see that e to the 3x would be equal to 0, but we know e to the 3x can never be equal to 0, or 2 plus 3x is equal to 0. So let's write this here. So 2 plus 3x is equal to 0. So this gives us now that we're stationary when x is equal to 0, assuming the function is defined for x is 0. And then this one would be now that x would be equal to minus 2 over 3. So they're the x coordinates of where this particular function would be stationary. So all we've done is use the product rule and then moved it on from there. So that's a nice straightforward example of where we have now an algebraic function and then an exponential function where we have a function of a function. Let's do another one. Let's say we have now y is equal to, and we'll have y is equal to 4x to the power of 5 multiplied by the natural log of 3x. So we have now here an algebraic function, 4x to the fifth, and then we have the natural log of 3x. Or if you like, we've got 4 lots of x to the fifth multiplied by the natural log of 3x. So what we can do here is call now this one u, and we can call this one v. Or if you like, you can call this f of x, and this is g of x. In terms of the notation, often in this particular course, we've got u and v. You will see though f of x and g of x. You might even have more functions multiplied by one another. So let's go ahead and set this up. If you want to, you can just simply now take these two functions. So if you want to, you can take this function and multiply it by the derivative of this one. Then take this function and multiply it by the derivative of that one. So it's the first function multiplied by the derivative of the second, plus the second function multiplied by the derivative of the first. I prefer to write it in a table such that we're showing full workings and we're not making mistakes. So what we're going to have then, u is going to be equal to x to the power 5. The derivative du by dx, so we'll have du dx and have u, is going to be 5x to the fourth. If we take now v, we've got the natural log of 3x. We looked at differentiating the natural log of 3x in the last video. So what we did, we wrote 1 over the inside function and we multiplied through by the derivative of the inside function. So this gave us now 1 over x. Again, if you haven't seen that video, please do check it out. That's dv by dx. So what we're going to do is multiply these two and add to it the multiple of those. So we'll have now dy by dx will be equal to 4 lots. So taking the constant out, we're going to have 5x to the power of 4 multiplied by the natural log of 3x, plus now we're going to have 1 over x, and I'll write it just here, 1 over x multiplied by now x to the power of 5. So we can see that these are going to cancel, so we can write now dy by dx will be equal to 4, and then we're going to have now 5x to the power of 4 multiplied by the natural log of 3x plus now x to the power of 4. And again, we can factor this. So let's go ahead and factor that. So we've got dy by dx will be equal to 4x to the fourth. Taking now the common factor of x to the fourth out, that will leave me now 5, the natural log of 3x plus 1. And that's now factored. So if we were asked to find out where this was stationary, we could set dy by dx equal to 0. So let's go ahead and do that. I'm just extending this on a little to look at some applications of differentiation. So let's say now we wanted stationary points, and this particular function now was defined for all values now, and let's say that x is going to be greater, let's go greater than 0. So let's say now that x belongs to the reals, so, and then we've got now x, and x will be strictly greater than 0. So let's put a domain on this. So what we'll do now is find where we've got stationary points. So stationary points, therefore we can write that the derivative dy by dx will be equal to 0. So we consider now right here that either x to the fourth is equal to 0, therefore that x is equal to 0, and we can see that x can't be equal to 0 in this particular case, because we've got now x greater than 0. So we can say now for this one, therefore x is 0, and we say that x can't be equal to 0 as it's going to be greater than 0. So what we're left with then is 5, the natural log of 3x plus 1 will be equal to 0. So let's do a bit of rearranging and we can get an exact value for x right here. So the natural log of 3x will be equal to minus 1/5. So all I've done is subtracted 1 divided by 5. So exponentiating both sides, or writing the exponential equivalent, we've got now 3x is equal to e to the minus 1/5. And then we can say the x-coordinate of the stationary point is 1/3 e to the minus 1/5. Or if you like, you could write this now as the x-coordinate would be 1 over 3 e to the power of 1/5. And that's just finding now the x-coordinate of a stationary point. And again, we would check that that was valid for the domain that we set, but essentially that is what we're looking to do. So we're employing the product rule again. We've used the chain rule at this part as we have a function of a function, and just gone ahead and found now a stationary point, or at least the x-coordinate of a stationary point. Let's now look at an exponential and a trig example. Let's go for y is equal to e to the 4x, and then we'll have now, let's go for sine of 2x, and we want now the derivative. We want dy by dx. So all I'm going to do is set up my u and my v, and I will let u be equal to e to the 4x. So u, we're going to have e to the 4x. If I find the derivative du by dx, so these u and v are just functions of x. If you like, you've got f of x, g of x, or h of x if you wish. So the derivative, using the chain rule, we're going to have 4e to the 4x. If we now take v, and v is going to be sine of 2x, we've seen that the derivative would be 2 cos 2x in the last video. So that now gives us dv by dx. All we need to do is multiply these two and then add to it the multiple of those two. So in general, we can say now that if y is equal to u multiplied by v, where u and v are both functions of x, which we can differentiate, then dy by dx, the gradient function by the product rule, will be v du dx plus u dv dx. So let's go ahead and do that. So dy by dx, we're going to have now the multiple of 4e to the 4x and sine 2x. So 4e to the 4x, and then we've got sine 2x, and we're going to add to that now the multiple of these two right here, which is going to be 2e to the 4x multiplied now by cos of 2x. So that now is our gradient function. And again, we could look at solving now for the stationary points. I'll just go ahead and factor that. So let's just factor that. So dy by dx, we're going to take a common factor. Let's take 2e to the 4x out. That's going to leave me 2 sine 2x plus cos 2x. So again, if you wanted to find stationary points where we've got 0, e to the 4x can never be equal to 0. We've seen that from graphing it. If we look now at e to the 4x, or any exponential curve, unless it's transformed in any way, the exponential curve looks something like this. So we're coming through up here, and when we'll have this point 0, 1. And we can see now that there's no curve in the negative part. And it's always going to be, we can say now that the domain, let's write this here, the domain x belongs to the reals, so any number can go in, and the range, we've got y is always going to be strictly greater than 0. We're never touching that x-axis. This is an asymptote. So if we're asked now to find the stationary point, we can say e to the 4x is never equal to 0. So let's just put, now, or turning point, stationary point, we can say dy by dx is equal to 0. We can say e to the 4x cannot be equal to 0. Therefore, the content of this bracket here would be. So we could go ahead and find a solution for this. So 2 sine 2x plus cos 2x would be equal now to 0. And we could look at finding the first solution. There will obviously be subsequent solutions, but essentially we can go ahead and just solve for one of these. So if we do that, subtracting cos 2x from both sides, we've got 2 sine 2x would be equal to minus cos 2x. At this stage we could divide by 2 and cos x, so we get sine 2x over cos 2x would be equal to minus 1/2. At this stage we could write that tan 2x would be equal to minus 1/2, just using basic trig identities. 2x would be equal to the inverse tan of minus 1/2, and then we could look at finding possible solutions given a specific interval. But you can see from there, that should be fairly straightforward. So depending on the domain that we're given, we could go ahead and solve now for stationary points. And that's one of the advantages of writing this now in factored form. So taking this back, if we got y is equal to e to the 4x multiplied by sine 2x, u is e to the 4x, v is sine 2x, or the other way around, go ahead now differentiate using the product rule, and then I factored if we, well, it could be helpful if we did. We'll finish with one more, and we'll look at a purely algebraic example. Let's go for y is equal to, we'll do something slightly different. Let's say we've got 5e to the x squared multiplied by the root, and we'll go for the root of x plus 1, and we wanted to find the derivative. My first rewriting of this would be now 5e to the x squared, and then we're going to have x plus 1 to the power of 1/2. So let's just do this, and we'll write that dy by dx will be 5 lots, and we might be asked to write this in its simplest form and look to find a single simplified fraction. So let's go ahead and set this up. So over here, what we're going to have now is u. So if we have now u, and we can say that u will be equal to x plus 1 to the power of 1/2. So we need to differentiate this using the chain rule. So the derivative du by dx by the chain rule. We differentiate the outside function, we leave the inside function alone and multiply through by the derivative of the inside function. So we're going to get 1/2. I'm multiplying down by the power, I'm rewriting the inside function, I'm dropping the power by 1 and multiplying through by the derivative of the inside function. So we have 1/2 x plus 1 to the minus 1/2, or we could have 1/2 root x plus 1, depending on how you want to write it. If we now take v is e to the x squared. We need the derivative, which is dv by dx. So we're differentiating the outside function, we're rewriting the inside function and multiplying through by the derivative of the inside function. And of course, when we're dealing with these exponentials, it's just simply a case now of multiplying the derivative of the inside function by the original function. So this is just 2x e to the x squared. Again, if that means nothing to you, please do check the video prior to this. So let's go ahead and rewrite this. I'm going to just write this now as the multiple of these two. And I'm going to have it now as e to the x squared. And now I'm going to have this divided by 2 root of x plus 1. So all I've done is multiply these two. I've rewritten this now, x plus 1 to the minus 1/2 as 1/2 the root of x plus 1. We're now going to add to that the multiple of these two right here, which is going to be 2x, then we're going to have e to the x squared multiplied by the root of x plus 1. So all I'm doing now is multiplying these two and rewriting it. Okay, let's now get a single simplified fraction. So what we've got then is dy by dx will be 5 lots, and I'm going to combine these fractions. So the common denominator now is 2 the root of x plus 1. So e to the x squared plus now we're going to have 2x e to the x squared, and then we're going to have now the root of x plus 1 multiplied. All of this is going to be multiplied by 2 lots of root of x plus 1. And as you can see now, this is going to tidy up quite nicely. We've got all of this now over the common denominator of 2 the root of x plus 1. So this is a simple case of adding algebraic fractions, which we've looked at in a previous unit on this particular course. So dy by dx, let's do some tidying. We've got now 5, and I'm just going to write it as 5/2. We've got 5/2. If I look here, what we've got now in the numerator is e to the x squared plus now 4x e to the x squared. I'm multiplying now the 2 and the 2, x e to the x squared, and then we've got now the multiple of root of x plus 1 and root of x plus 1, which is x plus 1. So all of this now is over the root of x plus 1. So let's go ahead and tidy this further. We can see that we've got now the common factor here of now e to the x squared. So we can write this, and this is a little messy, but hopefully it's making some sense. We've got 5e to the x squared over 2. That's going to leave me now 1 plus 4x, and then we're going to have now x plus 1. And that's what we're left with now in the numerator, and then in the denominator I've got the root of x plus 1. And you could of course argue that this could be outside in here. It really doesn't matter. Now can we do anything with that numerator? Let's go ahead and look at this. So dy by dx, we've got now 5e to the x squared over 2 the root of x plus 1. Now that's going to leave me here 4x squared plus 4x plus 1. Now that looks like it's going to factor 4x squared plus 4x plus 1. Let's see if we can factor any more. Dy by dx. We're going to have 5e to the x squared over now 2 the root of x plus 1. Now looking at this, this looks to be 2x plus 1 all squared. So that's what we wind up with, and we could write it like so. So if you're asked of that now in its simplest form, that is one way that you could write it. I mean, quite clearly you could write that as the half power in the denominator, but that's one particular approach that you could take. So as you can see, some of these questions get quite involved in terms of the algebra, but the basic derivative is just here. This is the derivative. All I've done is look to tidy it up and clean it up and get it now as a single simplified fraction, such that we have 5e to the x squared multiplied by 2x plus 1 all squared over 2 lots of the root of x plus 1 or x plus 1 to the half. So this may come up in an exam style question where you're asked to sort of tidy it up and make it look nice and clean at the end. But essentially that's all we're doing. We're hitting now at this point where we've got the derivative and then we're tidying up. So there we go, that's a basic introduction to the product rule. The product rule is used when we're differentiating the product of at least two functions. We might have more than two functions. We say that u and v are both functions of x. So if we have y is equal to u multiplied by v, the derivative dy by dx is v multiplied by du dx plus u multiplied by dv dx. Or if you like, the first function multiplied by the derivative of the second plus the second function multiplied by the derivative of the first. And we've seen that we can use function notation. In the next video, we're going to move on and look at the quotient rule. But hopefully for now, that's giving you a brief introduction before we move on to specific videos on trig and log and exponential functions.